All right, so we're going to get into section 1.5. Section 1.5 is on matter. We're going to revisit matter. Now, if you will recall, we we had we defined matter as having two properties. Matter has mass and has volume. Now, mass, really, I don't have a great definition for this because mass we define as the amount of matter present. Typically, though, in chemistry, we can just go straight to talking about mass in terms of units. In chemistry, our most common unit for measuring mass is the gram. Occasionally, we might use kilograms. Sometimes we might use milligrams, but gram is by far and away the most common. Now, for volume, typically in chemistry, even though it's not the base unit, we will use the milliliter. All right. Now, from mass and volume, we come up with another property, which is density. And of course, this was the subject of one of our experiments that we did in class, or that we did in lab, I should say. Density, right? Density is mass over volume. Right? Now, the SI unit for mass is the kilogram per cubic meter. But that's kind of impractical for us in chemistry. And so typically in chemistry, we say grams per milliliter, right? Now, related to this, though, is a concept called specific gravity. To find the specific gravity of a substance, we take its density of the substance divided by the density of water. Now, the beauty of using specific gravity is that it is unitless. So it doesn't really matter what units we're using for density when we calculate a specific gravity. As long as we're using the same thing, we're going to end up with the same answer. Now, a lot of times we will hand wave and say that the density of water is 1 gram per milliliter, but that's also not exactly correct. As you all found in lab the other day, it's typically less than 1 gram per milliliter, but that's close enough. Right. Now, if we have something, if we're stating the specific gravity of something, say that we find the specific gravity of a substance is 1.32, the way that we phrase that, since this is unitless, we would say the specific gravity is 1.32. Okay. Now, that's density. Let's also in this talk about temperature. Now, I'm actually going to flip pages for this because I want a lot of space to talk about this. Up to this point in your life, you have probably quite often measured temperature using the Fahrenheit scale. Right? Now, if we look at the Fahrenheit scale, water, of course, boils at 212 degrees Fahrenheit. It freezes at 32 degrees Fahrenheit. Okay. Now, a lot of people will look at this and say, that's completely illogical. That makes no sense whatsoever. But there was actually some logic behind how Dr. Fahrenheit set up his scale. Here's what he did with this. He said 0 degrees Fahrenheit. It's being the lowest temperature he could reliably create in a lab, which is ice in saturated salt water or ice in brine. Then he said, okay, 100 degrees Fahrenheit is normal human body temperature. Of course, we know now, typically we say that normal human body temperature now is 98.6 degrees Fahrenheit, but close enough. But of course, typically in the metric system, not in the SI system, but in the metric system, we will talk about the Celsius scale. All right. And in the Celsius scale, water boils at 100 degrees Celsius. It freezes at 0 degrees Celsius. Body temperature, of course, in there is 39.5 degrees Celsius. Now, this is all good and well for a lot of purposes, but sometimes, especially in chemistry and in physics, this scale doesn't work so well either. So we have a third temperature scale we will talk about, which is the Kelvin scale. Now, if we look to talk about the Kelvin scale, I'm going to backtrack a little bit to Celsius and say that there's a point on the Celsius scale, actually on any temperature scale, where, and this I will say is a theoretical concept, it's not something that we can actually achieve, but there's a concept called absolute zero. That's the point at which all molecular motion ceases. It is, in theory, or it is the lowest theoretically possible temperature. It's not actually possible to reach absolute zero, but we've gotten pretty daggone close to it. Now, in the Celsius scale, absolute zero is negative 273.15 degrees Celsius. Here's where the Kelvin scale is different. In the Kelvin scale, we set absolute zero as 0 Kelvin. By the way, notice that there is no degree symbol here. Kelvin temperatures do not have a degree symbol. So if 0 Kelvin is absolute zero, that makes the freezing point of water in Kelvin 273.15 Kelvin, or really most of the time 273 is close enough. And that makes the boiling point 373 Kelvin. Okay. Now, in this class, I will expect you to be able to convert from Celsius to Kelvin and Kelvin to Celsius. Fortunately, that one's easy. So degrees Celsius plus 273 equals Kelvin, or Kelvin minus 273 equals degrees Celsius. I do not expect you to know how to convert between Fahrenheit and Celsius. Okay, I'm not even going, there are formulas out there that take you to both, but I'm not even going to give them to you. That's just not something we're going to worry about doing. All right, so that's temperature. Now, also sort of related to this, but actually really related to this, because temperature is one way we measure energy, we can talk about the concepts of potential and kinetic energy. All right. Essentially, potential energy is energy that has the potential to do work. Kinetic energy is energy of motion. Now, oftentimes, or one, not oftentimes, but one good illustration we can use for this is we can look at, just for example, a roller coaster. All right, so we have a car. We have our roller coaster car up here at the top of the hill. Sitting up here at the top, it has a lot of potential energy, no kinetic energy if we model it as being stopped. Soon as it starts down the hill, we've converted potential energy to kinetic energy. Right? We get to the bottom of the hill, we have, for all intents and purposes, converted kinetic energy, converted all of our potential energy to kinetic energy, not really, but in a hand waving sense for this. And then, of course, we're going to go back up the hill. We've regained potential energy, go back down, convert back to kinetic energy. All right. That's the difference between those two. We will revisit that later in the semester. We will revisit energy. That is a good chapter 8 topic. All right, now the last thing, again, is something that I'm not going to talk about in a lot of detail because we have done a lab on it, and that is specific heat. Specific heat we define as being the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Okay. Now, in lab, we talked about the specific heat of water in terms of calories. Specific heat of water is 1 calorie per gram degree Celsius. Now, we have another unit that we use for energy that's actually quite a bit more common. Excuse me. Actually, quite a bit in more common use. That is the joule, Joule. 4.18 specific heat of water is 4.184 joules per gram degree Celsius. All right, so that's specific heat, and that gets us to the end of section 1.5.